Okay, the dynamic link architecture. Let me first say something about the status, from my point of view, of neural computation. The field is totally dominated, as you all know, currently by deep learning. The learning part of that is handled on conventional computing hardware, and the execution can be put on embedded systems that are very simple. So I have to make the blurt out whatever everybody here knows, that there is no need for neuromorphic computing at the current moment in time. So we have to look into the future, into general artificial intelligence after the model of the human brain, and I think that is a very important discussion point. The real issue is the scope issue. You know, current systems are either programmed, and the scope of the system is limited to what the programmer can imagine in terms of application, or they are learned on the basis of large data sets, which again set a very limited scope. That needs to be increased by orders of magnitude to encompass autonomous systems like autonomous cars with all the priority setting and all the contextual dependencies and so on, handling of eventualities of contingencies. I am sorry to make another rather provocative statement, which is conceptually, artificial intelligence has made progress for decades. This list of names is not complete at all, but all these names, their deeds go back to at least 30 or 40 years. And my take of the situation is there is a roadblock. There is a roadblock here. The situation is set up for an explosion. You know, the deep learning breakthrough has prepared the way for a totally new level of technology. There is a lot of public attention. There is a lot of funding poured into the system. With respect to the brain, there is a flood of experimental data, as Terry, if he's here, still here, has told us about yesterday, with breathtakingly novel methods. They are yanking tons of data from the brain, and the computing technology is going to be here, as witnessed by this conference. So what is the roadblock? In my view, the situation is like an overheated boiler, and all it takes is to pull the plug. What is the plug? Here's my answer. The roadblock is the neural code issue. I'm going to tell you what it is. It is the proper answer to the question, how does neural tissue in my brain represent the mental phenomena that I experience? You, as you are sitting there, have a clear view of the situation in which you are immersed. You forget that this is a simulation of your brain. You place your ideas out there. This scene is out there. But this whole scene, in all its detail that you can perceive, has been created by the neurons in your brain. Whatever you can mentally imagine is, of course, brain states. And so this is a very central question. How do neurons do that? And I think the current roadblock is that there are two prominent ideas about this, but they fall short of the correct answer. The first answer is bits. Bits have all the expressive power you can imagine. They are completely general. It is all in the hands of the algorithm that creates the bits or interprets them. But the whole intelligence is in the programmer's mind. And to create anything like a human-level visual system or an autonomous organism is beyond the economic power of mankind in terms of writing algorithms. That is the limitation of bits. And when you go to neural networks, classical neural networks, as we are all discussing them here, neurons are seen as logical propositions, any kind of logical proposition. Each decision in the system needs a dedicated neuron. Of course, thousands or millions of decisions at a time. But if you want the system to decide it's a dog, you need a dog cell. If you want to decide the system to grab an apple, you need a grab an apple cell, and so on. This is a bottleneck of this data structure. What is missing, which I've pointed out near to 40 years ago, is the concept of compositionality. Cognitive scientists know that. We compose the ideas we have in mind out of different aspects, out of different parts. We can glue different parts together. The glue is missing from this data structure. So as a consequence, the neural networks, as we know them, have a gross lack of expressive power. Just try to imagine a system that expresses the richness of the scene you are experiencing in terms of lots of individual logical propositions which have no connection between them. I defy you to do that. I'm running into people who claim they can do it, but of course nobody has done it yet. And one of the consequences is that deep learning needs too many examples. That's a gross limitation of that particular technology. So that is the neural code issue. In conclusion, I claim bits are too general, neurons are too narrow, and as a consequence, artificial intelligence is nothing but a shadow of human thought. Let's look at the human model. It takes 1 gigabyte of genetic information to create an organism, a human organism. And if you cared to create a nursery in terms of virtual reality, it would take a gigabyte of code to create that. We do everything to make the nursery, to make the environment of our children stable and simple. It doesn't take a lot of information. You still don't understand the interaction with the mother, but I don't think it would take a lot of information. And the amount of visual information that a child takes in the first 3 years is, if you can do the calculation, something like 5 eye blinks per second, 10 hours a day, 365 days a year, is 200 million eye blinks. That's not much by the standards of deep learning these days. And in this time, a 3-year-old child can grasp the environment just like you and I. We expect them to know what is out there, to think in terms of objects out there. They can navigate and manipulate this environment. They can act purposefully. If you have children, you're highly aware of that. They can speak, and they can learn from the inspection of an individual implement. You show them a TV remote control, and they know them all, in spite of changing color and shape and pose and so on. In order to make that possible, as roboticists don't fail to claim, the human system has to be embodied. It has to be in touch with the environment over a number of channels: vision, touch, hearing, proprioception, motion. And the condition for being sure of knowing what is out there, of being confident of the conclusions, is that these very different, logically very different channels agree with each other on the same representation. In order to play that game, you need a representation of the environment which can be in sync with all these different signals. So I look at a scene, I move my head, which is a motion signal, it's a proprioceptual signal, and that generates an expectation as to the perspective movements, and vision has to say yes to that. Yes, indeed, it is exactly what you believed. That gives us confidence that we know what is out there. We touch the things, and the agreement between sight and touch in that sense is the basis for learning. And the system has to be situated. It has to go through a sequence of states where all those different modalities are in sync with each other. They talk about the same environment from which attention has selected a little sector. So a probably superfluous slide in this conference here about implementation. The brain has 1.5 liters of volume, needs 20 watts, is massively parallel, is computing with analog signals, which are very slow. Speaking of energy, there's a very good reason for that. The neurons communicate by something you may call digital or semi-digital. The spikes are not synchronized. And the components are all very unreliable, which leads to the fact that there is a massive conflict with the classical computing style. Bob Caldwell said, don't work with a system, the components of which are unreliable. It's a nightmare. That's exactly what you have when you have a brain-like system. You have to go about it in a completely different fashion from ordinary computing. There is no determinism in the machine. It is impossible to know the actual state of the machine due to non-determinism and due to asynchronous operation. And the only thing you have to guide the machine is by global control parameters. So how can you go about it? You have to think about it in terms of control theory, you know, all poles to the left half plane. You have to think of the system as a dynamical system. Neural signals are continuous and are stochastic. And so ask the question, how come that the activity is not totally drowned in noise? Classical analog computers died because if you chain up operations, the system gets totally drowned in noise. So in order to prevent that, the brain trajectories have to be attractors. So almost all the Lyapunov along almost all dimensions of diversion from a trajectory, you must have negative exponential exponents, Lyapunov exponents, so that the trajectories are attractors. The stabilizing forces are, of course, feedback loops. Everything is immersed in positive feedback loops that stabilize what you have, and these forces are, of course, excitation and inhibition. Talking about the connectivity again, the synaptic values are stochastic continuous variables. And you may ask the question, it's a very serious question, how come that my memory is not totally corrupted by noise? I have memories that go back 50 years. How is that possible? With individual synapses, if you look at them with electrodes, they change from spike to spike. They seem very unreliable. So the only way out is brain connectivity must be an attractor. The forces there are cooperative interactions between neurons. Can I point? Yes, I can point. So this neuron here can only fire if it is immersed in a cocoon of other neurons that happen to fire at the same time, because it takes something like, once estimated by Moshe Abiles, 10 input spikes to fire a neuron. So a neuron can only fire in the context of co-firing neurons, and an individual connection can only grow if there are other connections that arrive at the synchronous time. So this is the kind of these kind of cliques must be the components of valid connectivity patterns. The whole thing is bridled in by competition. A neuron doesn't want to be overworked and makes sure that in an active state, there is a finite number of connections that are active. So the networks we are going to deal with are superpositions of lots of these cliques. The cliques are finite due to the competition, but they overlap. And so this reminds me of, if you have any mathematical inkling of topological systems, these cliques are like the open sets of a topological system. Now, the process by which networks are generated and stabilized is the process of network self-organization, which has been extremely well studied, both experimentally and theoretically, in the context of the early ontogenesis of the nervous system, for instance, the establishment of retinotopic connections or maps of orientation-specific neurons. It's a well-studied process, and it is amazing that in the field of neural computing, it is totally out of fashion to think about neural network self-organization. This is the process. I remind you of the information that goes into the brain. This is the process that is responsible for the establishment for the construction of a connectivity pattern in our cortex that takes a petabyte to be described, 10 to the 14 synapses, each taking something like 30 bits of address. That gives you a petabyte. It is a factor of 1 million of the information that goes into the brain and the information that you find in the brain. Of course, the Kolmogorov information is only gigabytes and not petabytes. The attractor nets in our brain are dominated by certain structural features, and here are just 2 types of attractor nets I would like to talk about. One is, is this actually working? Yeah, one is neural sheets, which are 2-dimensionally extended sets of neurons with local connectivity. That's a well-established idea in the neural community. Neural sheets, it sounds like a boring concept, but if you imagine that in each position there is a big choice of individual neurons that can be selected, you can see that there is a combinatorial multiplicity of sheets possible. And if you have 2, that's one type of network that's going to dominate. And if you have 2 such sheets, then a topological projection pattern between them is another such pattern. I have lots of experience with the establishment of these, like, for instance, in the early ontogenesis system. Now, with these 2 types of networks, I think one can build a visual system. Just to illustrate, here is, this refers to a face recognition system I've built 20 years ago in order to convince my colleagues that these network patterns dominate the brain. It is actually used in the European border control system, this face recognition system. So the idea is, we know that a face comes into primary visual cortex as a 2-dimensional array of local feature neurons. Now, take it seriously that there are lots of lateral connections in primary visual cortex, so believe me that it is a very tenable assumption that what is actually activated from the input is a neural sheet, not only neurons, but also connections between them that are organized as an attractor net. In order to recognize that face, I posit there must be somewhere in the brain, in infratemporal cortex, in the fusiform complex, must be another neural sheet with a model of that same face. A model that is homeomorphic in the sense that it contains with some precision the same types of local feature neurons in the same arrangement, in the same connectivity pattern. And in order to find out about this homeomorphy, you need this other type of connectivity pattern, which was introduced a long time ago by Charles Anderson, who published that with David van Esten, shifter circuits. It was the basis of the PhD thesis of Bruno Olshausen. And by the way, Charles Anderson was the thesis advisor of Chris Learsmith, who is probably still here in the room. So these networks here are switched on or are excited by the simultaneous presence of 2 homeomorphic nets here, making clear that this corresponds to that. Now take a small moment thinking about what kind of decision that is. There is no decisive neuron. You can add a neuron that lights up exactly when you see Barack Obama, but it's not necessary here. How is the decision taken? It's a collective decision by lots of neurons, thousands and thousands, each of which is in its own preferred cocoon of neighbors, neighbors within one sheet and the neighbor in the other sheet. It's a collective decision. I think that's what the brain is based upon. The details of this model have been published a long time ago, worked out in fine neural detail. This face recognition system is now certainly beaten by Google's FaceNet by an order of magnitude, I think. But if I wanted to which is a deep learning kind of structure, if I wanted to prevail, I would introduce submodalities that describe not only the texture, as this face recognition system did, but also the shape, the depth profile, the pose, the motion, the illumination, and so on, such that they interact in a coherent fashion, such that they amount to a parameterized model of the face, which is tuned to the input, such that all these modalities are all right, including identity. Now let me say a word about a concept that Hava talked about yesterday, abstraction or comprehension. 2 minutes. Cognitive science has always thought in this fashion. You comprehend a concrete object in terms of a schema which is homeomorphic to the object by having nodes, quote unquote, that correspond to the parts of the object and having links which correspond to the object internal spatial relationships. And the connection between the two is established by links that take care of the perspective motions. If you have, as a 3-year-old child, developed those parts here as object components and see for the first time a tricycle, you know as a child immediately what it is good for. It's a vehicle. It has a front, it has a back, it has these different parts you can put your hands on and your feet. And in a moment, you can construct a schema that represents the tricycle, and you recognize them all in spite of all changes in style. So let me come to my conclusion. The neural code of the dynamic link architecture sees neurons integrated into net fragments, into self-organized pieces of network structure. These are generated by self-organization. They have structure in being sparse and having consistent connections. Net fragments can connect into larger coherent nets if those coherent nets have the same structure. And each situation creates its own brain-spanning wiring pattern, which turns the brain into a specialist for this situation, so that your motor system can react to your sensory part under the control of your current priorities in an appropriate way. A little bit like Hava's statement yesterday, we have a different algorithm in different moments of time. The meta-algorithm in the terms of super Turing computing is, of course, the mechanism that generates those networks. So the good news for the current community here, the neuromorphic community, is that this is a totally homogeneous architecture with everything that is needed to realize an intelligent system. It is trainable without big data, I say incidentally, and it requires a gigantic data volume. So my conclusion is the mental state is coherently composed of net fragments. Our brain comprehends the world on the basis of homeomorphy. Thank you.
Thank you. Thank you, Christoph. We have time for a question. Yes, please.
So I'm having a little trouble following where the gigabyte of training information comes from. But I want to kind of back up from that a little bit and just ask, I see the model for vision that you described. I mean, how kind of have these schemas and the sort of kind of assemblies of components that build into a vision model. I have some trouble seeing how this approach scales to higher level cognition that most of our brain is focused on, as opposed to pattern classification. So can you talk a little bit about how this approach would map beyond just visual processing?
Vision is just one of the modalities that goes into the system of the brain that arranges the environment in geometric terms, in kinematic terms. There is a nice book by George Lakoff, a linguist, who goes through all kinds of cognitive phenomena and makes the statement, you can always relate them to geometrical situation. A clause is enclosed in a contract, and you think of something in a cup and so on. So I think what children develop is something that is tuned to a geometrical environment, and all the rest of their life, they project all the cognitive space onto that machinery. That's what I believe.
Wolfgang.
I wanted to address one point that you made, that deep learning typically requires tons of data. I agree. I think this was the case a few years ago, but if one looks at current research, for example, at last SNPs in December, one-shot learning and few-shot learning were kind of among the main topics discussed there, and there are many algorithms which can cope with this. So I think kind of machine learning is moving so fast nowadays that it's hard not to really categorize and what they can or cannot do. With a single sentence, obviously, and one has to be careful.
How do you go beyond the limit of needing a dedicated neuron for a decision? You have to train it. I'm talking regularly to groups that work on autonomous moving cars. I ask them, what difficulties see you ahead of you? And they all say, edge cases, unusual cases, objects we haven't seen before, situations we haven't seen before. What do? We need 10,000 examples. It's impossible to create them. I don't see, I'm aware of these developments. There is a number of papers that talk about one-shot learning. I don't think they break this difficulty.
Okay, thank you, Christoph, for your talk and the discussion.